In this video, we will explore the normal distribution. A normal distribution is a symmetric, bell-shaped distribution with a single peak. The peak corresponds to the mean, median, and mode of the data set, and the variation is characterized by the standard deviation. In order to classify a data set as being normally distributed, most of the data values must be clustered near that mean to create a well-defined single peak. As you move away from that peak, both left and right, the value should be evenly distributed, but also decreasing in frequency as you move away from the mean. There's a couple of different data values that can result in this combination. Once we know that something is normally distributed, we can use the 68, 95, 99.7 rule to figure out what percentage of our data set appears within a certain number of standard deviations away from the mean and from other standard deviations. This is called a Gaussian distribution, and it says that if something is normally distributed, 68% of the data values that occur in your data set will fall within one standard deviation both above and below the mean. 95% of the data values will fall between two standard deviations up and down. These are our usual values. And 99.7% of the data values will fall between three standard deviations up and down. There will be data values that go more than three standard deviations both above and below the mean, but there will be very few, if any. So 68% of your data set falls within one standard deviation, from a negative one to the positive one. 95% falls within two standard deviations. So within two standard deviations, both up and down, 95% of the data falls within those two values. 99.7% of the data points fall within three standard deviations of the mean. You can only use this rule when you're talking about exactly 1, 2, or 3 standard deviations away from the mean. An example of this would be a vending machine. Vending machines can be adjusted to reject coins above and below certain weights. The weights of a legal U.S. quarter is normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? So quarters, legally produced quarters, still have variation, and sometimes they do go outside of what would be considered normal or usual values. We've all had an experience where you put a quarter or a nickel into the vending machine and it just doesn't want to accept it. It's because it falls out of those preset weight values that are set in the machine. A weight of 5.81 is 0.14 grams more than the mean. This happens to be two standard deviations, right? 0.07 twice. A weight of 5.53 grams is two standard deviations below the mean. And so we're talking about weights from two standard deviations above and two standard deviations below the mean. And since it's perfectly two standard deviations up and two standard deviations down, we can use the 95% rule that says that if you are between two standard deviations from the mean, 95% of the data will fall in there. So about 95% of the legal quarters will be accepted. If 95% will be accepted, this means about 5% of legal quarters will be rejected. There will still be a few quarters that don't fall within the preset weight range, even though they are legally created. But what happens if you don't want to talk about from 1 standard deviation up to 1 standard deviation down, or even 2 standard deviations up to 3 standard deviations down? Then what we need to do is convert the values over to a z-score, also sometimes called a standard score. It's very easy to calculate a z-score. You will talk about the data value that you are referring to, subtract the mean, and then take that difference and divide it by the standard deviation. They could either give you the mean and the standard deviation, or they can give you the full data set and have you calculate, use either by hand or by calculator, the mean and the standard deviation. It is a conversion just like you would convert maybe from feet and inches to kilometers or centimeters. This is the stat world conversion, so that regardless of whatever your study is about, whatever type of numerical data you're collecting, you can convert all of those numbers, whether it be heights or weights or IQs, and convert it over to a z-score and use that 95, 68, 95, 99.7 rule. If you have a data value that's above the mean, you'll wind up with a positive standard score, normally referred to as a z-score. And if you have a data value that is below the mean, then that will result in a negative z-score. It is always the data value that you are exploring minus the mean. You don't flip them around to make sure that you get a positive value. Positive or negative values will occur in the z-score world. The Stanford Binet IQ test is a scaled test that has scores that are normally distributed with a mean of 100 and a standard deviation of 16. We want to find the standard scores, or the z-scores, for the IQ scores of 85, 100, and 125. So we will use our formula of the data value minus the mean, all divided by the standard deviation to get our z-score. For an IQ score of 85, that would be 85 minus 100 for a negative 15, and then we'll say negative 15 divided by 16 to get a value of negative 0.94. Z-scores are always rounded 2 decimal places. For the 100, we would say 100 minus 100, which is a 0, divided by 16. 0 divided by 16 is a 0. The mean will always have a z-score of 0. The standard score for 125 would be 125 minus 100 for a numerator of 25, and then divide by 16 for a 1.56. The 125 is a value higher than 100, which is our mean, so that must have a positive z-score. And the 85 is a value lower than our mean of 100, so it must have a negative z-score. Height of women is normally distributed with a mean of 62 inches and a standard deviation of 2.4 inches. What percentage of women are between 58 inches and 65 inches? When we're looking for areas or percentages, we'll have to not only convert to a z-score, but then take that z-score and measure the distance between the two of them, or sometimes from 1 to infinity. The textbook will instruct you how to do this with a chart, but we're going to use the calculator instead. If we want to figure out what percentage of women are between 58 inches and 65 inches, first we're going to need to figure out what those inches are in z-scores. 58 minus 62 is a negative 4. Divide by a 2.4 and I get a negative 1.6 repeating. And so that will round to a negative 1.67. For the 65 inches, we'll say 65 minus 62, that's 3. Divide by 2.4 and I get 1.25. So my z-score for the 58 inches is a negative 1.67, and the z-score for the 65 inches is a 1.25. Now I want to figure out what is the area between those two. We can estimate this using the 68, 95, 95 rule because it's about like a -2 to about a +1, but we want to know it exactly. So we're going to use one more calculator feature. You'll need to hit second vars to bring up the distribution menu and then select normal CDF. Once you select normal CDF, it will either pull it back out to the main screen if you have an older version of the calculator, or open up a new screen on a newer version of the calculator. We're going to enter the lower z-score for a -1.67, and then enter a comma on the old version of the calculator. On the new version of the calculator, you'll just go to your upper z-score and enter a 1.25. This is what it looks like on the older version. On the newer version, it will say lower, and you'll enter -1.67, and it will say upper, and you'll put 1.25, but then do not change any of the other values on the screen. From then, you'll either go to calculate and hit enter, or you'll hit enter from your main screen, and you'll get a decimal that will always be less than 1. Sometimes they ask for the answer in decimal form 4 decimal places. So they may say 0.8469 would be your answer. In this case, they wanted to know as a percent. So we're going to change this to a percent by multiplying by 100. And then we'll round to the nearest tenth. So about 84.7% of women are between 58 inches and 65 inches. If we're talking about a percentile, that's a specific type of area question where that we're talking about, I want to know from that value down. You've seen percentiles on any type of standardized test that you might have taken. The SAT is a very popular one. When you get your SAT scores, they'll give you a raw score, but they're also going to give you a percentile. That percentile says you did better than that percent of people that have taken the test. And the SAT people do exactly what we're going to do here. To find a percentile, you'll need to find one z-score that corresponds with a data value, but then you're going to want to know about all of the possible z-scores below it, and so we won't have a lower value. So that means negative infinity. And for negative infinity, we're going to use a -9999. Cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a 20-year-old man with a cholesterol level of 190? And then we'll look at what cholesterol level corresponds to being in the 90th percentile. In A, we're essentially asking, if you have a cholesterol level of 190, what percentage of people do you have a higher cholesterol level than? So higher is not always better, right? So having a high cholesterol means you essentially beat out all of the other people in the cholesterol level test, but that's not a good thing. For B, we're going to look at what would your cholesterol level have to be for you to have a higher cholesterol level than 90% of the other people in your population. Again, not a good thing. Let's start with A. The standard score for a cholesterol level of 190 is going to be about a 0.29. 190 minus the 78, 12. 12 divided by 41 is about 0.29. Then, to find the percentile, we'll go to second vars to bring up the distribution menu and select normal CDF like we did before. We'll enter in the lower score for the lower z-score a -9999. Since there is no lowest, we want to know if I'm the highest, but I don't want to put a stop point for my lowest. For the upper, we'll put the 0.29. Press enter or calculate, and then you're going to multiply that value by a 100 and round to the nearest whole number. That would be 61. So you would be in the 61st percentile. If you had a cholesterol level of 190, essentially your percentile is saying that you have a higher cholesterol level than 61% of the other people in that same population. Let's look at B. What cholesterol level corresponds with the 90th percentile, the level at which treatment then may be necessary? We'll go back to second VARS and enter the distribution menu again. And this time we're going to select inverse norm because I know what percentage of people I want to be higher than. I just don't know what that score is going to be, right? So nobody says I tested, at the 90th percentile for weight or on the test or for height. You see this often when infants are born and they're measuring progress. You want to know what the actual length of the baby is. You want to know what your actual score is, not just how many people you beat out. Well, click on inverse norm, and if you have an older version of the calculator, you'll go back to the main screen. If you have a newer version of the calculator, you'll go to another menu where it says area, and that's where you're going to put in the percentile as a decimal. So on the old calculator, I just say 0.9. On the newer version of the calculator, in the area section, you would put 0.9. Then hit enter or calculate, and I get a 1.2815 ... That's the z-score that corresponds to the cutoff. So I would have to have a value on the cholesterol level test that generates a z-score of 1.28. But again, nobody says, hey, I have a cholesterol level with a z-score of 1.28, or I got a z-score of the test of 2.5, right? You would say what the value actually is. So we're going to have to go one more step to find out what that value is. Round the z-score to the nearest hundredth, so it would be a 1.28. And then we're going to use the formula, the mean plus the z-score that we just found times the standard deviation. So here, the mean is 178 plus the z-score that we found, 1.28, times the standard deviation of 41. And that cholesterol level would be about 230. So if you had a cholesterol level of 230, then you would have a higher cholesterol level than 90% of the other people in that population group. So when doctors take the test and they see, oh, you have a 230 or a 240, they know right away you need treatment. Whereas if you had a 199 or a 201, it may be high, but not high enough that they are now beginning to worry and needing to put forth treatment.